So today I'm going to try and show that, okay, so today's goal is to show that PIDs are UFDs. So the goal for today is so PIDs. So UFD is a unique factorization domain. And this is where every element, non-zero element, non-zero, non-unit, can be written as a unique product of irreducible elements or prime elements up to associates. Okay, and so let me start with a little lemma here. So here's a lemma that we'll need. So let R be a ring. R be a ring. It's kind of a messed up R. Okay, and so let P in R be prime. Then if P divides A times B, this implies P divides A or P divides B. Oh, this is all messed up. Okay, those little dots aren't going away for some reason. Let's see if I do that. Oh, there. Okay. Okay, so proof. Let's do the proof of this. This is not a hard proof. But let's just kind of recall, this would be a good time to recall how we define something to be prime. So recall that P in R was prime if and only if this ideal generated by P was a prime ideal. Is a prime ideal. Okay, that's how we defined something to be prime. And I guess this is a maybe just as good as a definition up here. Okay, so okay, so suppose. Okay, so suppose now P divides A times B. Okay, then what do we have? So then we have AB. This is equal to 0 in this ring. Okay. But we proved that R mod P was a domain. R mod so for every prime ideal, R mod P is a domain. Let me just go back to that. Okay, so this means that A bar is equal to 0 or B bar is equal to 0. And this proves P divides A or P divides B. Okay, do you guys see how that works? All right, so all right. Okay, so so now I want to say a little bit about the factorization into irreducibles. Okay, so this is something that we're going to need. We need this part. So this is something we need for the uniqueness. So this part here is needed to show factorizations of elements into primes. Prime elements, let's say prime elements, is unique. Okay. So this whole like divisibility thing. So what we're gonna do is so once you have well, and let me think. Can I do that part right away? So maybe I can do that right away. Yeah, let me do that proof. Okay, so let me do a theorem. So let R be a ring. And suppose that that P1 through PR and Q1 through QS are prime elements. So if P1 P2 dot 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 to PR is equal to Q1 Q2 QS, then R is equal to S, so there's the same number of factors, and up to relabeling, P1 is an associate of Q1, P2 is an associate of Q2, etc. Okay, so this is what we mean by unique factorization. So if you have a factorization, then the two factorizations have to be the same up to associates. And remember, two things are associates if they differ by a unit. So, like 5 and -5 are associates. Okay, in say the integers. Okay, so let's do the proof. Yeah.
These prime elements don't have to be distinct. They can be repeats.
They can be repeated, yeah. Possible repeats here. Yeah. Yeah, that's true. Okay, so let's do the proof. Let's do induction. On the maximum of R and S. Okay, so in the case, and I guess we should say that these are, these should be non-empty too. Oh, I went back a page. Non-empty collections. Okay, in the first case, right? Then essentially we have P1 is equal to Q1, and I guess you're done. Okay, so there's really nothing to the base case. Okay, so the inductive step is now, so the inductive step. So suppose the proposition is true. It is true for max RS is equal to n minus 1, or, S is equal to M less than N, and prove it is true for max RS is equal to N. Okay, so okay, so what we do is if and this is really not so difficult, right? So you just do if P1 P2 through PR is equal to Q1, Q2, QS, right? Then, okay. Then we'll have something like this. Then P1 divides Q1, Q2, QS. So we have, P1 divides Q1, P2, or P1 divides Q2, or P1 divides QS. By relabeling if necessary, so without loss of generality. So when I do WLOG, that's without loss of generality, right? We can assume P1 divides Q1. So we could just relabel the Qs if we wanted to, right? Reindex them. Since Q1 is irreducible, or prime and irreducible are the same thing. Well, I guess if this were a PID, prime and irreducible were the same thing. But since Q1 is prime, was someone going to ask something?
Yeah, I said we're not in a commutative ring, right? That's why you said that.
We are in a commutative ring. All rings are commutative unless I say otherwise.
Okay, you said earlier it could be repeats. I would think we wouldn't have any if you could just move them around, or
you could, right? So like what's one with repeat? 8 is 2 to the third. So which is 2 times 2 times 2.
Oh, I'm sorry. We didn't put the exponents on there. My bad. Okay.
Yeah, exactly. We didn't put the exponents on. Yeah. So yeah. And since Q1 is prime, so we have that that P1 and Q1 are associates. Okay, and so now, so I guess we have to assume that, okay, so R is a ring. R needs to be a domain. So this thing here needs to be at least a domain. For what I'm going to do next. Okay, let's see if we need anything else. So now we can cancel, right? So this means that this thing here means that P1 is equal to U times Q1, and so this gives us that P1, P2 up to PR is equal to. And so now we have, maybe I should have done this. U inverse P1, Q2, and then we have QR or QS. I think we had like this. We did that with S's, right? And then we get to cancel. So this is where I used, let me put it in blue, I guess, because we were doing this hypothesis in blue. Since it was a domain, we get to cancel those two. Okay? And so this gives us that P2 through PR is equal to U inverse Q2. That's still a prime element because I multiplied by a unit, QS. Okay? And now we get to imply the inductive hypothesis. Now we apply the inductive hypothesis. Hypothesis to conclude. All right, and that's it. That's the uniqueness of factorization. So we really use nothing. Okay, so this is like one of these proofs where you're like, you don't really have to think at all, right? You just kind of like do it. All right. The harder part of this, that a PID has unique factorization, is the existence of a factorization. Okay, so okay, so and I guess here we also use that these elements are prime, not just irreducible. Okay, so all All right. So let me do a lemma.
Did you probably say it, and I might have missed it, that the cancellation requires the that it's a domain? You probably said
Yeah,
that.
yeah. That's equivalent to it being a domain. So like here, if you have AC is equal to BC, right? This implies that A minus C or A minus B, C is equal to 0, right? And so this tells us that A minus B is equal to 0 or C is equal to 0. So this is what allows you to cancel. Since if C is not equal to 0, C is not equal to 0, then A is equal to B, right? So this is what proves the cancellation law, right? So you're allowed to cancel non-zero elements in UFDs. Or sorry, in domains, not UFDs. You're allowed to cancel non-zero elements in domains like this. So maybe I shouldn't write that there, but the idea is that if you have the lemma is that if R is a domain and C is not equal to 0, then AC is equal to BC implies that A is equal to B. Right? So this is the proof of this. All right. So all right. So now I need to say a little bit about Noetherianity. Okay, and then I need to do this for the purpose of showing that factorizations exist. Talk about this. Exist. Okay, so let's prove that. So let me just say what. So recall that a ring R is Noetherian if every ideal is finitely generated. Okay, there's two other conditions that we need. Okay, so the two other conditions that we need are the following. So there's a theorem. Okay, so let me give you a definition. So a ring R satisfies the ascending chain condition okay, or this is also, we'll just abbreviate this, the ascending chain condition. Let's put it like this way. This is equal to the ascending chain condition, if and only if for all, so here we're only going to look at countable chains, right? If and only if for all chains of ideals, every chain of ideals terminates. I1, I2, right? So there exists some n, some natural number n, bigger than or equal to 1, such that for all I and j, bigger than or equal to n, we have I is equal to ij. Okay, so this thing maxes out, right? So so at some point, right, you're not going to get any more new elements. This is hot as balls. Sorry. It's like a heater in my back. Okay. So yeah, so at some point you're going to max out, and then all the ideals become the same. Okay. So all right. So then the theorem that I want to prove is that Okay, so let R be a ring. So the following are equivalent. Okay, so 1, R satisfies the ascending chain condition. So, okay, every non-empty collection of ideals has a maximal element. And let me just put like a little warning here. Not necessarily a maximal ideal. So not necessarily that the ideal modulo, the ring modulo of the ideal is a prime. A maximal. Just meaning, you know, R mod M is a field. Okay, and then the third thing is that every ideal in R is finitely generated. Okay, so this is these are important equivalent conditions. Okay, so if you say a ring, so a lot of the times people call the first one, they usually, so, okay, depending on who you're talking to, right? 1 and 3 are probably the most commonly referred to as a Noetherian ring, right? So all of these, you know, so all of these here are equivalent to the ring R being Noetherian. Okay, so let me show you how to use this first, okay? And then we'll go to proving these things, okay? So first we're going to apply this, the application. Oh. Undo. There we go. Okay. So this will be the application of the ascending chain condition to factorization. Cool. Okay. So okay. So let's do the theorem. So let R be a Noetherian domain. I don't think we need a domain even. Let R be a Noetherian ring. So I'm trying to, by the way, I'm trying to follow the convention that lowercase, so that words with people's names in it, when it's used as an adjective, is lowercase, which I think is a very nice convention. Okay. So let R be a Noetherian ring if F in R is non-zero and not a unit, then F is a product, then let's say there exists irreducible elements pi n irreducible such that f is equal to pi 1, pi 2 through pi n. Okay, so this is saying that you can factor something into a product of irreducible elements. Okay, and the proof of this is pretty simple as well. Once you have Noetherianity, this one, knowing to prove this, I think is the hardest part. I think of this whole business is this part here, and I guess knowing the correct hypothesis for this to work. Okay, so let's do the proof. Okay, so if f is irreducible, we are done. Okay, so if f is not irreducible, if not, then by definition, we can write f is equal to f1 times f2, where neither f1 nor f2 is a unit. Okay, and now we're just going to kind of continue this process. Okay, so if f1 is not irreducible, then f1 is f11, f12. Okay, with neither f11 nor f12 a unit. Okay, and we're just going to continue this process. Okay, and so at this stage, we can write, f as equal to f11, f12, f2. Okay, and then we kind of continue in this process. To get, f, this is contained in f1, this is contained in f11, and then it would keep going like this. And so by Noetherianity, this terminates. Okay, so and then eventually you're going to get to an irreducible element. Okay, so and that's at least for the f1 term. So you go down, and so I'm just kind of like going to sketch what happens, and I'll let you guys try to convince yourself that this works. Right? Is that here we had f, right, and it splits into f1 and f2, right? Or let's do f2 and f1. Okay, and then this thing splits up into f11, f12. Okay, and then you could keep going down this way, right? And this thing could continue, and this thing could continue. Okay, but what we've essentially shown is we've shown that every path in here, every path to the bottom of this tree has finite depth, right? This is by Noetherianity. Because once you go down this tree, right, okay. So once you go down, you get one of these chains that's at the top. So one of these chains up here, right? And so by Noetherianity, these chains have to terminate, right? So and each bottom thing is an irreducible factor, and so each so there are finitely many this implies that there's finitely many paths to the bottom. And hence factorization into irreducible, into finitely many irreducible factors. Okay? So that's the idea. Okay? Do you guys have questions on this?
Yeah, can we just scroll up for a second? What was like, so this was, I understand that we got this ascending chain via Noetherianity.
Mm-hmm.
But what was,
yeah, this terminates.
It terminates, right?
Yeah. So we got this by supposing that this didn't turn into an irreducible. So like, as long as the first thing doesn't turn into an irreducible thing, you can keep building the chain, right? But you know that you can't go forever, right? Because of Noetherianity.
Okay. Yeah.
Right. And so when you do this factorization, right, you don't have to just focus on a single element here. You can focus on all the elements. And then it's just like you did in like middle school or whatever, grade school, right? Where you just take it and you factor it into a bunch of pieces. And Noetherianity tells you that this tree will have finite depth. So no matter how you go, you'll go to finite depth. But once you get to the bottom of this, you'll reach an irreducible element.
And we're getting all of the these ideals contained this way, like ascending this way, yeah, by that idea of like to divide
divisibility by divisibility. So it's like this one divides. So it's like here you have this one. This divides this. So the ideal generated by this is contained in the ideal generated by this. That's what this thing says, the top piece. Okay, and then you have this one divides this one. So it's like, so to divide is to contain, is what some people like to say. Okay, and so anytime you go down the tree, you're going to have a divisibility and hence a containment.
Okay, cool.
But it doesn't show that the factorization is unique, just that such a factorization exists.
Right. Okay.
Okay. So yeah. So now we're done, right? So what we've done is here. Okay. So now let me just kind of like summarize and say this out loud about why we're done with PIDs. As long as you believe the equivalence of the Noetherianity conditions. Okay. I mean, you actually don't even need 2. You just need to believe that 1 and 3 are the same thing. Okay. Because we showed that in every PID, right, is finite. The ideals are finitely generated, right? And so, so a PID is Noetherian. Okay. Also, we've shown that in a Noetherian ring, primes and irreducibles are this. In a Noetherian ring, everything can be factored into a product of irreducibles. That's this theorem. In a PID, I stated previously, and I did half of it, that irreducibles and primes were the same thing in PIDs. And then we showed that earlier today is that if you have a factorization into primes, right, then the factorization is unique. Okay, so maybe I can say this. So we are done showing PID implies UFD, right? So PIDs are Noetherian. Okay, all the ideals are finitely generated. Okay, prime is equal to irreducible in PIDs. That's something that we showed. Okay, and then we also showed that factorization into primes into primes is unique. And then we showed that Noetherians in Noetherian. I'm not following my convention. I messed it up here. Okay. In Noetherian rings, non-zero, non-unit elements factor into products of irreducibles. Okay, and so hence it factors into a product of primes in the case of PIDs. All right, so that's it. Okay. So so now let's take care of this Noetherianity business. Okay, so okay, so so I'm going to show that these are equivalent. I'm going to do as much as I can, and then I'm going to leave the rest as an exercise. So I don't think I'll be able to finish all of it, but it's not so tough once you know what implications to do. So let me kind of just tell you what we're going to do. So so first, let's do. We're going to do the proof strategy here. Is so 1 is equivalent to 2. Okay, so the strategy. Oh. Is going to be 1 if and only if 2. And then we're going to do that. So 2, let's see what we have here. So then we're going to have the ascending chain condition, which was which one?
1, wasn't it?
1. Okay, so 3, we're going to do 3 implies 1. And then we're going to do, I think 2 implies 3. Right, so these are the elements of the proof. Okay. Okay, so so for 1 implies 2, 1 if and only if 2. Okay, so let's do so the ascending chain condition is the same thing as an existence of a maximal element. Okay, so proof. Okay, so this is we're going to show that ACC implies exists maximal. Okay, so let's actually do this other one. Let's do it this way first. Okay, so so what we're going to do is we start with a chain, and then we're going to show that it terminates. Be an ascending chain. Okay, so what we're going to do is we're going to let S be the collection of these ideals. I greater than or equal to 1. Be the collection of ideals. So by the existence of maximal element, maximal, so then S, then there exists some n such that In is maximal. But this terminates the chain. So this thing seems way stronger than this condition that there exists a maximal ideal among all subsets of ideals, non-empty subsets of ideals, seems super, super strong, right? Okay. So
wasn't that for any ring?
For any Noetherian, so it's just a condition, right? And so we're showing two conditions on the ring are the same. One condition is the ascending chain condition. One is the condition that, okay, I'm going to define blah, blah, blah property to be, for every subset of ideals, there's going to be an ideal in there which is biggest among the ideals in that set.
Okay. Last
Among
Friday.
the ideals in that set. It doesn't necessarily have to be a maximal ideal overall, right? But among the set, it has to be maximal.
Oh, last week we just proved that rings have maximal ideals, period, right?
Yeah.
Okay.
This maximal is not the same as that maximal. Okay? This maximal is just maximal among the set.
Right.
That maximal is maximal out of all of them.
Right.
All right. So let's do the other way. So ACC implies there exists a maximal element. Okay. So what the idea is to construct an infinite chain. So the idea is suppose not. So let's let S be a non-empty collection of ideals. So suppose that it doesn't have a maximal element. Suppose there is no element. Okay. So then what we'll do is you pick I1, an element of S, right? And so by definition, by a hypothesis, right, there exists some I2 in S with I2 containing I1. Since I1 is not maximal, right? That's what it means to be not maximal. It means that there's something else containing it, right? And then you just kind of by non-maximality, right? And then you just kind of repeat this process. To get I1, I2, I3, right? And so this is an infinite ascending chain. This infinite ascending chain gives a contradiction. Gives a contradiction. Okay, does that make sense? So it's like if we didn't have a maximal element, if there was never a maximal element, right, then you could just take one, and there's always going to be one above it, and there's going to be one above that one, and so on and so on. That's going to give you an infinite ascending chain, and that's a contradiction if you suppose there's no infinite ascending chains. Okay, so that proves that part. Okay, so now let's suppose that okay, so let's do every ideal is finitely generated implies the ascending chain condition. Okay, so what we'll do is, so you let I1, I2, so let this be an ascending chain. Okay, then what we'll do is we'll take I we'll take it to be the union of all of these. And then here, okay, so we know that this thing is equal to this. So this is by the finite generation hypothesis. Okay, so we know that these guys here, AI, A1 through, so the union of all these ideals, it's an ideal because it's a chain, right? And then since every ideal is finitely generated, this ideal has to be finitely generated. Okay, but we know that since AI is in the collection, AI is an element of A of Ni for some Ni. Okay, then what we'll do is we let N be the maximum of N1 through, oh, let's see, let's do M. Mi. M1 through Mn. Okay, and so then this proves that this ideal here, A1 through An, well, this is contained in In, which is contained in, well, A1 through An. So, which proves the chain terminates at In. Okay, so that's how we get there. Okay, so for the last part we need to show that that maximal existence of maximals implies finite generation. Okay, so the trick, so I won't do this completely, is to consider the set of J ideals in R such that, so what we do is we let I be an ideal, and we need to show it's finitely generated. Is finitely generated. Okay, so then we take the set of ideals which are contained in J, or contained in I, and that J is finitely generated. Finitely generated. Okay, so we look at this set, and then let M in S be a maximal element. Okay, so the exercise is to show that M is equal to I. Okay, and that proves that M will be finitely generated. Or no, actually not M. So I mean, if it's if not, you know, consider M union, you know, some element X, or the span of this, I guess. And then this thing here will be a finitely generated ideal contained in, and so here X is in I set minus M, right? And then once you throw in that extra element, that's going to be in there, and that'll give you contradiction. So I guess, yeah. So the idea is to show that M is equal to I. What were you going to say?
I was just going to ask, could you also do like a contrapositive? Suppose you had an ideal that wasn't finitely generated, and then you just look at the ascending chain of ideals where you just keep adding on one of those generators.
Yeah, I'm sure something like that would work, right? Okay. So I would try it and then see if it works. I'm not sure. Yeah, I would try it. So I'm going to stop the video here and let you guys go, and then I'm going to stick around for questions.
Cool.